Alright, so we've talked position time graphs, we've talked distance, displacement, speed, and velocity. Let's now look at a velocity time graph. So starting from position time, we have somebody's position that's going, let's call it forward in a positive direction for a while, hits, after 10 seconds, hits 5 kilometers here, right there, and then goes back to 0 kilometers. So they're going forward and then going backward. All right, now we can tell here that this has a positive slope and this has a negative slope, and the slope on a position time graph is going to tell us velocity. Why? Because we have a change in position over a change in time, and that's literally the definition for a velocity. I'll call that an average velocity right now because, well, it looks for over that period of time. Anyways, all right, so we're going to look at the velocity time graph for this portion. Let me zoom out a little bit. We have this already ready to go. So for this first part, we got 5 kilometers in 10 seconds, so that's half a kilometer per, or sorry, not 10 seconds, 10 minutes. Half a kilometer per minute, and that velocity is constant the whole time. Just like this is a straight line. The slope doesn't change, so the velocity doesn't change. And on the way back, we're also going 5 kilometers in 10 minutes, but the opposite direction. So the opposite direction, we deal with a negative sign, and we have a negative velocity. Again, it's constant for that time. But what if our velocity is not constant? In fact, let's look at a situation where it's not constant. Maybe it's sloping upward, it's increasing, we're accelerating, right? We're speeding up. So we start at some velocity here. This looks like just shy of 20. We'll call that V0, velocity at time 0, or V0, or initial velocity. And we end at some VF, V final, up there. All right, and that happens over, here it's 30 seconds, happens over some delta t. Now this is a graph, it's linear. Now every linear graph can be explained by y equals mx plus b, the slope-intercept form. Thank you, math teachers. And here, our y variable, the one on our y-axis, is velocity. That output, let's call that final velocity. And m is our slope. X here is time. And b was that y-intercept. Now the y-intercept here is our initial velocity, v0. All right, so that initial velocity at time 0. Great. Well, this slope, guess what? That has a name. The rate at which we change velocity. In fact, if I rearrange this a little bit, minus v0, I get final velocity minus initial velocity. I'm going to divide by time equals that slope. That change in velocity over that change in time, that's called acceleration. I'm going to abbreviate it here because I'm lazy. So we have acceleration. So the acceleration is the change in velocity over the change in time. Great. All right, so that gives us a relationship we can work with. How quickly is the velocity changing? We're asking for acceleration. We're asking for the slope of a velocity time graph. But actually, this equation is going to come in handy too, because sometimes we just want, hey, how fast is it going now? Because we already have the acceleration, and we know the initial velocity. So that's going to come in handy. But realize these two equations are the same thing, just rearranged for convenience sake. Acceleration is the change in velocity over change in time. Some call that just the definition of acceleration. All right, that's a better A there. Definition of acceleration. This is the same equation, just solved for final velocity. Sometimes you want to know, hey, how fast is something going? Acceleration times time, plus however fast it started at. All right, so in summary, we have the definition of acceleration, change in velocity over time, which is the slope of a velocity time graph. So however steep this is, that's however much it's accelerating, how much the velocity is changing over time, right? Now, if your velocity is changing, your displacement, their position time graph, or if you're graphing displacement, that's not going to be linear anymore, because as you go faster, you should be covering more distance per time later on than you were in the beginning, because you're literally going faster now. So that velocity, the slope is changing, that slope is increasing, because you're getting faster. So now the displacement graph is going to be curved. And if you're not changing velocity, if your velocity is constant, then your position graph is linear, and your velocity graph is, well, just, well, constant. It is that value.